So let's imagine for a second that you'd like to use some cloud storage to store some sensitive data. And this storage provider gives you an API. It lets you read at indices like 42 like it's an array, lets you store secrets in there, lets you, write stuff. And the implementation here is just to encrypt the data. It's really simple. You can also get your data back by decrypting the data. However, the indices involved, they can't be encrypted because the read-write indices need to be sent in the clear in order to do the access. Therefore, they can't depend on any secrets. And so doing things like some access to cloud storage where the index is a secret and not a publicly known value, this is disallowed, and it's disallowed to preserve the confidentiality of your secrets. Now, if you did want to do something like this, access the storage with an index that depended on a secret, there's an algorithm for that. It's called Oblivious RAM. The implementation builds on the simple encryption implementation of non-oblivious RAM. But there's an extra layer of indirection that garbles the indices that lets you do the secret access, and it lets you have read and writes that do depend on secrets. So more flexible, secure storage API. Now, this talk isn't necessarily about ORAM specifically. It's about a new language we developed called Lambda Obliv. Lambda Obliv is designed to let you implement oblivious algorithms like ORAM. So using Lambda Obliv, you could implement this API that gives you this read and write access to storage where the indices can be secrets. So Lambda Obliv can do more than just implement ORAM. It has applications broadly for secure databases and secure multi-party computation. Lambda Obliv innovates on type system design, semantics, and proofs for probabilistic programs and probabilistic properties. We released with our paper a publicly available implementation that you can use right now to play with new oblivious algorithms. And the moral of the story is if a type checks in our language, you get a strong probabilistic security property. You don't have to think about truth tables and things like that, or probabilistic distributions directly. So in describing our work, I'm going to first go over some basics of ORAM. These are generalizable little toy problems that are descriptive of most oblivious algorithms. Then I'm going to go over the actual design and proof of our language and type system. So digging into ORAM and oblivious algorithms, first I want to talk about the security property that they want to satisfy. So a standard non-probabilistic security property that a lot of oblivious algorithms satisfy is called MTO, for memory trace obliviousness. This is an adversary model where the adversary can see public values, the program counter, memory and array access patterns, and they can't see secret values that you pass around in your program. And the MTO property is that you can't infer secret values from public observations. It's a relatively straightforward non-interference property, given this stronger adversary. So let's look at a baby non-secure ORAM. By baby, I mean the index space is 1 bit, is 0 and 1. And it's not secure, so it's kind of wrong to call it ORAM, but we'll build on this to get to a correct ORAM. So this program uploads 2 secrets to the storage. S0 and S1, we store them in indices 0 and 1. Here's what the adversary can see. They see the indices in the clear. That's fine. I want to read at some secret index S to my private variable R. The adversary can see the array index, and now they just learned my secret, and this violates traditional MTO. So the fix to this in a non-probabilistic setting is relatively straightforward. So here's baby trivial ORAM. It's secure. The program is the same, where we upload our data to indices 0 and 1, and then we read out all of the data, and the adversary here, again, just sees indices 0 and 1 fly by. We have them in local storage R0 and R1, and we perform this atomic mux operation. So mux is going to look at the guard, which here is S, and if S is 1, it'll flip the branches, the second and third argument, and if it's 0, it'll leave them the same. A pair is getting returned, and we're just looking at the first thing. So here, the adversary can't see what's going on with the mux. They can see control flow, so this mux needs to be atomic, and that's an important part of this program. So this program's great. It satisfies MTO. It's secure, but it's inefficient because it requires a linear scan of the whole database. So in order to do better than linear time for secure access using secrets, we need to weaken our security property to something that's more probabilistic. So in our paper, we describe a new security property called PMTO, for probabilistic memory trace obliviousness. Here, the adversary can see the same stuff, New in the computation model is random values, like coin flips. The adversary can't see those, and the promise is the same. The adversary can't infer secret values from the things that they see. But here, inferring things about secret values is now a distributional notion, which I'll get to. So here's baby tree ORAM. This is a probabilistic algorithm that satisfies PMTO. And when this is generalized to full tree-based ORAM, you get logarithmic time performance rather than linear, which is great. So this algorithm, has a different setup phase than the deterministic setting. So first we flip a random coin. Remember, coin flips the adversary cannot see, they're secret. And then we scramble what we're going to store at indices 0 and 1 based on that coin flip. So if the coin came up 1, we swap S0 and S1, and if it came up 0, we leave them alone. We upload that to the database. The adversary doesn't know the result of our coin flip, so they don't know the way in which they're scrambled. And now we can access our secret index S by XORing it with the secret bit. All right, so this has a right functional correctness property, retrieves what we want, and it's secure. And in particular, it's secure in a strange way in that there is a direct data dependence between the secret that we're trying to hide, which is S, and the thing that the adversary sees, which is the index. So just a straightforward data dependence analysis or property is not going to be relaxed enough to let this program go through. But it is secure in a probabilistic sense, in that it satisfies PMTO. And to quickly convince ourselves of this, we can look at a truth table. This is all the possible outcomes in our setting. Imagine, so here the adversary is seeing the B, X, or S thing fly by in their observations. Let's say they saw 1 for that result. Now this is the possible universes that could have happened. The secret is still uniformly distributed, and they don't see the hidden random value B. And if they saw 0, right, and so the secret is still hidden. That's very important. It could be 0 or 1. If they saw a 0 for the XOR, it's still 0 or 1, so that's great. That's the encoding of the fact that the adversary doesn't learn anything. But a funny thing is happening, which is really crucial to getting ORAM and oblivious algorithms correct, and also makes it tricky or sort of easy to get them wrong, is that this value B is now considered a sensitive value. So initially we flipped it, it's just a coin, it's not tied to any secret, but now it's intimately correlated with S after having observed this XOR. So say outputting B after this XOR, this would be very problematic. It'd be equivalent to leaking the secret. So the design of Lambda Obliv is set up to let you implement these tricky kind of ORAM things while preventing things like releasing B after that XOR, which would be problematic. So there's, to kind of say it in more words, the fundamental design challenge in Lambda Obliv, it's a really tight design space. We need to allow for direct flows from uniformly distributed secrets to public values. So that's a kind of an unusual thing, but you need it to implement ORAM, while at the same time prevent revealing anything that's ever correlated with a secret. So this is tricky. So in solving this design challenge, the first thing we do in our language is we introduce a new type called a flip type. So this flip type is what you get when you flip a fresh coin. Flip types are affine, and we'll get into Affinity very soon. They're also uniformly distributed always, so anything at flip type is always uniformly distributed. And they encode secret random values, so they're considered secret for the purposes of, say, direct information flow. This R thing is a region annotation. Our paper introduces a notion of probability regions. These are elements in a joint semilattice, and we'll explore those again in a second. But the key idea behind regions is that values in the same region may be probabilistically dependent on each other, and values in strictly ordered regions are guaranteed to be probabilistically independent. And this independence constraint is important for the type system to be sound. So we have flip types for things that aren't necessarily uniform, or things that, I guess we'll see examples that use this. We have normal bit types with a region annotation and a standard information flow label. The region here is just tracking dependence on random values that came from flips that started with regions. In our language, we include standard features like references and functions. You need these to implement expressive algorithms. In terms of expressions, here's the generate a new flip expression. You have to pick statically a region annotation that you're going to flip that coin in. And then here's the two most important additions to the language that are kind of scary and derive the rest of the design. So these are escape hatches through sort of standard invariants that are absolutely needed to implement ORAM. They cause a ton of problems. And a lot of the techniques in our paper are kind of simple and clever ways to account for the problems caused by these two expressions. We'll see it through examples. But cast P is like a safe declassification. So this takes a flip type, these are secrets, to a public bit value. So it's a safe declassification. That happened in the baby ORAM when we revealed the XOR. Cast S is an escape hatch for the affinity tracking of the type system. So flips are affine. Cast S lets you treat it as if it's not affine. So you need both of these. And now the question is, how in the world do you guarantee PMTO in a language that has these features? And then after these sort of very special things, we have the usual operations over bits, reading and writing references, conditionals, and functions. So these are our escape hatches. And how do we deal with these while maintaining PMTO? So first, the two key features in the type system that do this are affinity and probability regions, and I'll go over them separately. So here's a really simple contrived program in our language that has these escape hatches like cast P. So I'm going to flip a coin, call it B1. I'm going to cast it to a public value, and I'm going to output it. All right, this is OK. A similar thing happened in the baby ORAM example. I'm going to build on this example. I'm going to flip a second coin in a different region. I'm going to mux between B1 and B2, call the result B3, and then I'm still just going to output B1. So I'm kind of doing nothing with that second line. That's OK. But I could also output B3. So B3 sort of looked at the secret. It looks like in a data-dependence way. Swapped these two coins maybe based on the secret. But I get one of the two coins back. And if I show you either of those coins, it's going to be 50-50. You don't learn anything about the secret. So that's OK. What's absolutely not OK is doing both of those things. So if I show you B3 and I show you B1, now you can learn the secret. So again, I'm going to go to a truth table. And I'm going to zoom in on what happens if, when we saw B3, we saw a 1. So this narrows down the possible universes to these 4 rows. Next, if we look at B1 and say B1 came out as a 0, there's only one possible universe where that happened, and it's where the secret was exactly 0. Now I've learned it. So that's problematic. So the way we fix this is we invalidate the ability to use B1 after that mux. And we do that with affinity. So one of the key rules in our type system, I'm going to visualize like this. Affinity, which is to consume the branch values, B1 and B2. These are at flip type, which are treated affinely. So a standard affinity tracking type system will take care of this for us. So if we go back to our example, our type checker will look at the uses of those branches, B1 and B2, remove our access to variables B1 and B2, and now we can't write this last line. It'll be rejected by our type system because B1 is not accessible. So affinity gets you almost all the way there with a language that has these escape hatches, but there's still one kind of plug that needs filling, and the solution to that is these probability regions that work in tandem with affine types. So here's another example that you can write in our language. So B1 and B2 are fresh coin flips. B3 is going to be, I'm going to swap B1 and B2 based on the outcome of B1. Here I'm just kind of shuffling coins around. That seems kind of innocuous. But notice the cast S thing. This is the escape hatch from the affinity check. So although B1 is consumed, cast S lets us use it again because of this escape hatch, and you need that to implement ORAM. And then this next line, we do a mux on the secret, and we either return B3 or a fresh coin flip. Now revealing B4 is not OK, and the main reason it's not OK is that B3 is not a uniform coin anymore. It has a skewed distribution, whereas the other coin flip does. So observing a, say, 1 or a 0 may skew the adversary's knowledge towards starting to know what the secret is. And affinity doesn't solve this. So if we play our affinity game, we see we use some branches. We remove access to some variables. We use B3. We remove access to B3. And we still have a problem, even though affinity is not going to do it. So the real issue here is a probabilistic independence semantic requirement, which is not satisfied by this mux. So if it was the case that each branch and each guard was probabilistically independent, then B3 would still be uniform, and this program would be OK. So we approximate this semantic probabilistic independence check through a region ordering check. So the second rule in our type system is to check that the guard and the branches are related with a strict ordering in the probability region order. And then going back to our example, this type check will fail because we flipped the coin B1 in region R1. R1 is not strictly less than R1 itself, so our type checker will rule out the program at this point. And I want to say something a little more about this region, or this region ordering and what it means semantically. So a lot of us are familiar with standard non-interference. There's a semantic notion of dependence or non-interference on values. B1 depends on B2. And this generalizes naturally in a static type system with some lattice-based approximation for dependence, where the semantic notion of dependence is reflexive and transitive, and you have this nice reflexive and transitive relation in your static approximation. Now, if we were just looking, let's see, the property we care about is probabilistic independence. Now, probabilistic independence is symmetric, but it's not necessarily transitive, and it's not necessarily reflexive. So if you were to approximate just this property with a lattice, you would be saying two probability regions are independent if their meet is bottom. This is like the lattice version of two sets being disjoint. This check is symmetric and not necessarily reflexive or transitive. But this, so you might be tempted to use this as an approximation for independence in your next language. The problem is, as the program runs and your adversary sees more things, you're constantly conditioning on knowledge that is learned by that adversary. So you don't just need to be independent, you need to be robustly independent with respect to prior revelations and possibly future revelations to the adversary. And this conditioning is what results in a strict ordering on regions as the sound thing to do when you're type checking static approximations of probabilistic independence. So I'm out of time. I'm going to skip through a bunch of stuff. We did a case study on tree ORAM. I want to say quickly, our theorem is that typing implies PMTO. Our proof is really not straightforward, and it's worth looking at if you're in this area of research. We use an alternative mixed semantics, which mixes operational and denotational methods, and we even cooked up a new probability monad that lets you talk about conditioning a lot more directly. And there's a pretty tricky semantic proof invariant for flip values that's worth looking at. I want to quickly advertise, so there's some prior work, but I want to advertise a talk tomorrow at 2:43 that also solves PMTO for ORAM via program logic. That'll be an exciting talk. I encourage everyone to see it, and I will stop there because I'm out of time.
Questions?
Very nice work. Could you go back to the example where you motivated affineness? Yeah. So in this example, I'm not exactly sure why you actually need affineness. Could you not just do this by dependency tracking? I mean, the point is that the first output clearly depends on B1. So the second output, if you output B1, there's a risk that you would, well, actually the first output depends on both S and B1, and the second output is directly B1. So just by dependency tracking, you would know that if the adversary knew both, it could probably infer something about S.
Yes, you're absolutely right. And the answer to that question is this is not a terribly representative example of the issues. Let's see, let me put it another way. To implement ORAM, you need this cast P thing. You have to have it. So you need this escape hatch from casting from secure stuff to public stuff. And you can do it kind of any way you want. So the first two examples, right, you could reveal B1. You need to be able to do that. You need to, you need to also be able to reveal B3, but not both. And a standard dependency tracking will fix you in one direction or the other. And there's also, for the purposes of information flow, these are all considered secrets. And there's this universal escape hatch of secrets into publics. So it's just tricky, yeah.
Hi, so you mentioned, first off, great work. This is really interesting. You mentioned that you relax the requirement on affineness for cast S. How does that not leak information when you output it? Or do you prohibit outputting things that rely on cast S? How does that work?
That's a great question. So the only thing you can throw to cast P is something uniformly distributed that started out uniformly distributed, and when you reveal it, it's uniformly distributed. So there's nothing learned ever by a cast P. Yes, and cast S is moving a secret random thing to a secret non-random thing, and then you can never cast P after you've done a cast S. Yeah. Great question.
So I have a quick question when the next speaker sets up. So of course, with these systems, the challenge is putting those annotations in the right places. Have you looked into it all to slicing? So you put some annotations where you want to definitely be secret, and then checking where, inferring where you should put the other annotations.
Right, so your question is about type inference and how you get them right.
Slice inference, basically, or region inference.
Yeah, region inference. So I believe our implementation can infer regions just based on the program point. It's usually how you want to do it anyways. You want them to be as fresh as possible, but if you're in a recursive loop, you have to reuse the same region because it's a static approximation. So we didn't have much region inference problems in doing our examples and pushing them through the implementation, but I'm sure there's examples where implementation won't do enough, and there's probably more work to do there. Yeah.
Well, thanks. Let's thanks David again.